Hello and welcome to this short talk on gradient-based quantification of epistemic uncertainty for deep object detectors, which is joint work of Matthias, Rottmann, Marius, Schubert, Hanno Gottschalk, and myself. This work deals with 2D bounding box detection on camera images, where each predicted instance is assigned an objectness or a confidence score, which represents the level of trust the object detector has in each of its predictions. This confidence score is an important quantity since it determines what actually remains as a prediction, and is therefore responsible for the errors that the object detector makes, that is, false negative and false positive detections. Moreover, this quantity tends to be miscalibrated, which means that assigned probabilities are not reflective of the statistics of the network's accuracy. This can have detrimental consequences in downstream tasks when employing object detectors in safety-critical environments. Methods for quantifying the uncertainty of the prediction can be used to address these issues. Whenever such a method depends exclusively on the network output, it can be used in object detection through application to each instance. Examples include any uncertainty of the class distribution or sampling-based approaches such as MC dropout or deep ensembles. The situation is different, however, for methods relying on shared DNN features such as hidden layer activations and gradients. The source of uncertainty in this work, originally investigated in the classification setting, is the self-learning gradient of a pre-trained object detector given X as an input, predicting a class distribution Y hat, and therefore a pseudo-label Y bar. We want to compute such a quantity for each detection, Y bar J, for example, this one. We deal with the complications of having multiple predictions per input and the LP nature of common regression loss functions by taking as a prediction candidate anchor proposals indicating the same box Y hat J. These obtain Y bar J as the pseudo ground truth signal. The scalar magnitude features obtained from these self-learning gradients per instance in a post-processing manner. In order to do so, we fit a lightweight classifier discriminating true positives versus false positives, a so-called meta-classifier, or a slim regression model estimating the intersection over union directly, a so-called meta-regression model. This leads to a prediction with alternative, improved confidence assignments to each individual box. We evaluate how well different methods separate true positive from false positive predictions, and find that our method performs on par with other uncertainty quantification methods, such as MC dropout or a deep ensemble. Adding gradient features to such output-based uncertainty features consistently yields boosts in separation capability. This indicates non-redundancy between gradient and output features. In this slide, regarding the combination of detector and the meta-classifier as one unit, we can study the resulting detection performance over different thresholds. We find that the meta-classifier separation carries over to object detection, leading to a more stable performance as compared to the score baseline. Moreover, confidences of meta-classifiers turn out to be well calibrated since meta-classification can be regarded as a kind of multivariate recalibration. One highly important question concerns the computational demand of calculating a gradient per predicted instance. We found that computation can be parallelized across predicted boxes per input. Then, a theoretical analysis of the number of flops required showed for a broad class of models that computing gradient features compares favorably to sampling dropout or sub-ensemble features. Ongoing and future work include investigations of gradient-based uncertainty in the light of active learning and the automated detection of label errors in object detection benchmark datasets. Furthermore, we are working on an efficient method of computing pixel-wise gradient scores in semantic segmentation. Thank you for your attention. In case you have any questions, we would be happy to chat with you at the poster session. Thanks.